We were talking about really phase changes, I think, last time. And we talked about really sort of the transition between, obviously, our three phases: solid to liquid to gas, and then obviously backwards going that way. And again, as we go from solid to liquid, that is the process of melting. Freezing would be taking it back from liquid to solid. Going from liquid to gas is evaporation or vaporization. Condensation is, again, going from gas to liquid. Shooting from solid directly to gas, skipping the liquid part, is sublimation. And coming back there the other way is what's known as deposition. We talked about it also in terms of sort of energy required to kind of do all these things. Again, from our solid to our liquid to our gas, those are all endothermic processes. So you got to keep putting energy or heat in to do those transitions, and heading the opposite way, going from gas back to liquid, back to solid. Those are all exothermic processes, which requires heat and energy basically to be released. So if you think about sort of gas molecules flying around, they release some of that energy, they slow down, they basically kind of clump together, if you will, fall into liquid. And if you continue to remove energy, they will become solid. We talked specifically about sort of the amount of energy required to do nothing more than really changing the phase of something. So when we go from solid to liquid, for example, that is the delta H of fusion that we use. And it also goes back the other way. And remember, the delta H of fusion is the energy required really to do nothing more than take a substance from the solid phase to the liquid phase, or backwards from the liquid phase back to the solid phase. Remember that that does occur at the same temperature. So for example, I think we talked about water, and that is 0 degrees Celsius where that occurs. And exactly at 0 degrees Celsius, you basically have both phases in equilibrium with each other. You have solid and liquid sort of happening at the same time. Again, not till you get a little bit above 0 degrees as you get liquid, a little bit below 0 degrees, you get that solid, but exactly at 0, which is the normal melting point or freezing point, for example, of water, we have both phases happening. So when we use the delta H of fusion, as we did in a calculation, I think it's like 333 joules per gram, something in that ballpark. That is the amount of energy to take, for example, ice at 0 degrees to liquid water at 0 degrees. Again, not changing the temperature or anything like that. We also have one for the sort of other transition, if you will, going from liquid to gas, or gas back to liquid, and that's the delta H of vaporization. And that's the same idea. This transition occurs at the normal boiling point, is where we transfer, obviously, from liquid to gas or backwards. Also at exactly that temperature. So if we take water again as the example, that's 100 degrees Celsius. So exactly at 100 degrees Celsius, we have, again, both phases happening at the same time. And that is the energy, for example, to take liquid water at 100 degrees over to basically steam at 100 degrees, which is gas version, or backwards. Remember that the value is the same in terms of that. So for example, the delta H of vaporization for water is like 2260 joules per gram. It is a positive value, right? Because it's endothermic as you go from liquid to gas. It is a negative value because it's exothermic as you go from gas to liquid. So it'd be negative 2260 if you're going the opposite direction. We kind of put these together with a heating cooling curve that we were sort of looking at, and we did a sort of a sample calculation as well. And again, if you had something like ice here, and this was, say, liquid water, and this is steam, which is obviously the gas version, and this would be approximately 100 degrees Celsius, and this right here would be 0 degrees Celsius. And again, when we look at this going from ice upwards to steam, that is a heating curve, and a cooling curve would be coming back the other way. Anywhere where we have those transitions, that is where we use our either delta H of fusion or delta H of vaporization. It is a flat line, which indicates that the temperature is not changing, but the phase is. So again, this is the area where we would use our delta H of vaporization and our delta H of fusion here. Remember that anywhere sort of on this curve where we are kind of increasing, not really a flat line, kind of increasing, which means that we are changing the temperature on those spots, but all the way through those spots, it is the same phase. And if we wanted to calculate the heat for those particular areas, that is where we used our specific heat equation that we learned way back when for those type of calculations. The important part, again, as we talked about last time when we were doing sort of the calculation, like normal, when we use our specific heat equation, we want to make sure we always do the final temperature minus the initial temperature, because that's going to give us either the positive number or the negative number. And also important is the specific heat capacity. Remember that the specific heat capacity for liquid water is that 4.184 number. But if it is like ice or steam, the specific heat capacity is like only 2-ish or so. So it does change depending on the state of that substance. So you want to make sure that if you happen to be, up in this area, that you are using the correct specific heat capacity. You would not use, again, that 4.184 number. You use like that 2 number that we saw the other day as well. So that's an important thing. Now, remember, if we did like we did a calculation where we kind of went, from the bottom to the top, you basically could just do each of the sort of steps there along the way, get the energy required to do each of those sort of steps as you come up the curve or even down the curve. And to get the total amount of energy, we just add them all together. So all the energy steps are basically just added together, and that gives us our total amount of energy. Any questions on that there? Okay. So the next thing we're going to talk about is intermolecular forces. We talked a little bit about last time as well, the difference between intramolecular forces and that is the force within a molecule. That holds it together. So again, if you took just one water molecule, what we're talking about really is these bonds that we see here, the bond between the oxygen and the hydrogen and the oxygen and the hydrogen. Those would be intramolecular forces. That is really our covalent bonding that we're talking about here. Now, when we talk about intermolecular forces, those are the forces that hold one molecule together with another. So that is the force. It basically holds two entire molecules together with each other. And that could be two of the same molecules. It could be two different molecules, but it's really how a whole molecule sort of interacts with another. So again, if we took two water molecules, it is the force that basically holds together this one water molecule with another, and that would be our intermolecular force, which would be obviously this attachment right there. So intramolecular forces are usually like covalent bonding, electrostatic attraction that we see in ionic compounds, and intermolecular forces are the ones that hold one entire molecule together with the other. Again, as we talked about as well, these guys are always weaker than an intramolecular force. So intermolecular forces are always weaker than intramolecular forces. And again, as we talked about, what happens when we start to heat something like water is we actually will break this bond that holds the entire water molecules together. And that allows this entire water molecule to break off and go, say, into the gas phase, and this one to go into gas phase as well. Again, if it was opposite and the intramolecular force was weaker, we would actually see each individual water molecule basically break apart as we create hydrogen gas, oxygen gas, which clearly doesn't happen when you boil water. So we get that sort of weaker intermolecular force that basically breaks apart. So what we're going to really focus in on here is intermolecular forces, and pretty much all intermolecular forces has basically the same sort of connection, the same way that they interact with each other. And it is a very simple sort of idea that the positive side of one molecule is essentially attracted to the negative side of another. So it's basically a opposites attract situation. And that's pretty much the basis of all intermolecular forces as to how they basically interact with one another. Why is intermolecular forces sort of important? A couple reasons. One reason is it accounts for melting points and boiling points. So depending on how strong the intermolecular force is, as to how high or low your melting point or boiling point may be. So for example, if we had a really strong intermolecular force here, that would pretty much translate to a high boiling point and melting point, because it would take a lot more energy to get those molecules apart from each other. And that would again translate into that higher temperature for both the melting point and boiling point. If we had a weak intermolecular force between two molecules, that also would account for a much lower melting point and boiling point, because they're basically held together by a pretty weak force. It doesn't take a lot of effort to basically get them apart from one another, and it would translate again into a lower melting point or boiling point. The other thing that intermolecular forces really account for, in addition to those things, are basically things like solubility and how molecules mix with one another. And as we'll talk about a little bit more in the next chapter, if there are molecules that you want to, for example, mix together, if they both use really the same type of intermolecular force, they will really mix really well together. So if you pick something that uses, say, hydrogen bonding that we'll talk about, and something else there uses hydrogen bonding, and you put them together, they're able to really interact well with each other, because they're basically doing the same type of interaction as they do with themselves as they could do with another type of molecule. But if you get together two things that are vastly different in terms of how they interact with each other, in terms of their intermolecular forces, then they also are going to have a very difficult time maintaining interaction with one another, and they typically will be insoluble in each other and really not mix really well. So intermolecular forces play a really important role in a lot of those things: melting points, boiling points, how basically substances are not able to interact with one another. It's really all based on these different types of intermolecular forces. All right, so let's take a look at some of these here. Actually, there we go. We'll kind of draw some of it. So the first type of intermolecular force that we want to talk about is one that is what is referred to as dipole-dipole interaction. And if you remember, dipole we saw when we were talking about bonding and polar molecules. So polar molecules, if you remember, have a dipole moment, which means that they have overall an unequal sharing of electrons in that particular molecule. The result of that is they get this dipole moment, which basically means there is a side of the molecule that's more positive and there's a side that's more negative. So that's basically what the dipole moment, right? That dipole moment is like those arrows that we were talking about when we were doing bonding, right? Points to the more negative side, right? And this is the more positive side of the molecule. And because of that, what happens is you have a molecule that has a fixed positive side and a fixed negative side to the molecule. And when that gets together with another polar molecule that also has a positive and negative side, that allows those guys to interact really well with each other through the positive side of one and the negative side of another. And dipole-dipole interaction is really the interaction that we see with polar molecules interacting with polar molecules. Now, this could be the same polar molecule interacting with itself. This could be really two different polar molecules interacting with each other. But these are guys, we'll use dipole-dipole interaction or dipole-dipole force, two polar molecules. It is also the ones that do not typically have the ability to hydrogen bond. And we're going to talk about what hydrogen bonding is. But typically, you know, the guys that can hydrogen bond will hydrogen bond, but these guys do not have the ability necessary to hydrogen bond, but they'll use dipole-dipole interaction. So whenever two polar molecules come together, and again, it could be two of the same, two different, because they always have that fixed positive charge and negative charge in the molecule, they are ready to basically interact with each other always. That is a fixed sort of separation of charge because it is polar. Sort of a relationship that we also see like this is sometimes referred to as, there's another sort of interaction which is known as ion dipole interaction. And ion dipole is pretty much what it sounds like. It is an ion and a polar molecule coming together. So this is when an ion and a polar molecule comes together. And we see this, for example, when we dissolve something like sodium chloride in water, right? We take, say, sodium chloride in water. Basically, the sodium will break apart into sodium ions. The chloride will break apart into chloride ions, and water that is polar will basically surround it. So in this case, the oxygen of water, which is negative, will surround this guy. And the hydrogen of water, which is positive, will surround this ion. And that is our ion dipole interaction. It's basically what happens when you take an ionic compound, put it in water, is pretty much that sort of reaction. Now, if we took a, you know, like a positive guy here, we'll do, so we have PF3, which is a polar molecule, right? It has an unsymmetrical geometry. It's got the dots on the central atom between fluorine and phosphorus, right? Which one should be more negative? The fluorine side, right, should be more negative. This is more electronegative, which should draw the electrons towards itself. This guy should be more positive. So when you get a couple of these guys together, again, these guys would use dipole-dipole interaction as, again, the sort of positive to the negative side there of these molecules will come together. Any question on dipole-dipole? Dipole-dipole is a relatively strong sort of interaction. But there's actually a sort of a stronger interaction that also is really a version of dipole-dipole interaction. And under sort of dipole-dipole interaction is another type of interaction, which is known as hydrogen bonding. So hydrogen bonding is really a type of dipole-dipole interaction. And it is a bond between, in order for it to hydrogen bond, you need a bond directly between and either nitrogen, oxygen, or fluorine. And if we look at nitrogen, oxygen, and fluorine on the periodic table, that is our upper right corner there, with fluorine being the most electronegative. So these are three really electronegative elements. So when it binds with hydrogen, what it creates is a pretty polar bond that happens. So it creates a pretty polar bond, which allows it to do its interaction. So that is what we see with water, for example. In water, we obviously have our bond between oxygen and hydrogen, and we have hydrogen directly bound to oxygen, which means it can participate in hydrogen bond, where oxygen being more negative, hydrogen being more positive. And again, if we get a couple of these water molecules together, negative and positive, we have a hydrogen bond that forms between the hydrogen in one, in this case, and the oxygen in another. If we take something like NH3 hydrogen bond. NH3 can hydrogen bond. We have a bond between hydrogen directly attached to a nitrogen, which is going to create that polarity that we need. And it can hydrogen bond. It could hydrogen bond again with another NH3 or even H2O. Now, just because something has hydrogen, it doesn't mean that it can always hydrogen bond. How about if we look at this guy here? This guy has a lot of hydrogens. Can it hydrogen bond? The answer is it cannot. So that hydrogen is not attached to nitrogen, oxygen, or fluorine, which is what is necessary for it to be able to hydrogen bond. The hydrogen in this case is actually attached to carbon. And we talked about carbon and hydrogen. Carbon-hydrogen bond is a electronegativity difference of about 0.4, which means this bond is non-polar, which means there is no separation of charge, right? Non-polar means that they're sharing the electrons equally as a whole. And this would be a non-polar molecule, also symmetrical geometry, right? Everything on the outside is the same, so it would be non-polar. So even though this guy here has a bunch of hydrogens, it cannot hydrogen bond. So sometimes people think, you know, as long as I see a hydrogen sort of there, it has the ability to do the hydrogen bonding, but it does have to be the right type of hydrogen, and the right type of hydrogen can be identified by it being attached directly to either a nitrogen, oxygen, or fluorine to allow it to hydrogen bond. Any questions on that there? Yeah.
I don't know, for some reason, it was like, I didn't really want on each side, but that's fine, as long as it's like nitrogen.
Yeah, so it doesn't need to have that sort of nitrogen or oxygen or fluorine there. And it does need to be sort of polar over all the molecule as well. That also kind of helps you out. Because really what we're talking about here is sort of that positive side of one, negative side of another, but that group is really important to either have that NH, OH, or kind of HF sort of group that's involved. Other questions? Now, in terms of strength, this is a really strong intermolecular force. So somebody has the ability to hydrogen bond. That is really the strongest intermolecular force that you could have. Now, let's talk about this guy that we did scratch out here that cannot hydrogen bond. He has to be able to do something. And really what he's able to do is what is referred to as dispersion forces. And dispersion forces, and obviously on the last one there for hydrogen bonding, this is really used for polar molecules. And polar molecules that obviously have the ability to hydrogen bond. So obviously hydrogen bonding or those for polar and polar molecules that have that ability to hydrogen bond. But dispersion forces, on the other hand, are really the type of intermolecular force that we see for nonpolar molecules. So this is really our nonpolar molecules. and nonpolar molecules, how they really interact with each other. And it is really the weakest type of intermolecular force that you could have. And it's the weakest type of intermolecular force because they are typically temporary forces. So these are typically temporary forces that develop. So there are a few different ways that it can sort of happen. One way is what is sometimes referred to as a dipole-induced dipole, or an ion-induced dipole. So what does that mean? It means that if you have, for example, a nonpolar molecule that basically has no charge. So there's equal spreading of all the electrons over the entire sort of surface. And if, say, a polar molecule happens upon it that has a positive and negative side, when they get next to that nonpolar molecule, what's going to happen is the electrons in the nonpolar molecule are going to decide, I want to get away from that negative side of that polar molecule. And temporarily, what's going to happen is you're going to have sort of a shift in the electrons of that nonpolar molecule where they will go away from it and temporarily gain a positive side and negative side in this nonpolar molecule and this polar molecule. And now they have a way to temporarily sort of interact with each other. You could also do that, obviously, with an ion, would make the same idea. You know, if you had an ion and a nonpolar molecule, the electrons, in this case, would go towards this positive ion, and temporarily that nonpolar guy will now gain a negative charge where they could kind of temporarily sort of interact with each other. These are temporary sort of fixes because as those guys sort of move away a little bit, the nonpolar molecules electrons are going to kind of reset and come back to its normal sort of configuration. And now it won't have that positive negative charge and it has no way to hold that. That is why, for example, when you mix something like oil and vinegar, right, which is polar and nonpolar, right, it'll mix for a while, but eventually it will all sort of settle out. Same thing, oil and stuff like that, right? You can mix it, it'll kind of mix, but eventually it will separate out. They can, for a very short period of time, sort of interact, but they have no way to maintain that interaction over the long period of time. So they're not able to maintain it because as soon as that nonpolar kind of comes back, it's going to break apart and maybe some new interactions will form and stuff like that. The other way that we can see this happen, and probably more common, and sort of what we see in, say, something with nonpolar and nonpolar molecules together, is eventually what could happen is if we have, say, two nonpolar molecules to start with, and electrons are obviously moving around. And if all the electrons decided to, for example, in this molecule, vacation over here to the left-hand side of the molecule, that is temporarily going to create a charge in this nonpolar molecule, which if it is still sitting next to the other nonpolar molecule, the electrons in this guy will go, oh, now there's a positive charge. I want to go this way and separate it to that side. Now, the second nonpolar molecule that normally doesn't have a charge will gain a charge. Our first one still has its charge. It sort of gained temporarily. And now, again, they have a way to interact with each other. The ability of an atom to sort of move its electrons over that one side or the other is what is sometimes referred to as polarizability. And that's the ability basically of the electrons in a molecule basically go one way or the other, and to basically separate out. Once these electrons decide to sort of reset, they'll kind of come back to as normal. And once again, here they sort of lose that ability to interact with one another as they go back to sort of equal sharing of electrons. So polarizability is really that ability of it to kind of shift one way or the other. Yeah. It's different from polarity, and it's a good question, is what we're talking about here in these type of molecules are, and these are like non-polar molecules pretty much, is they are not carrying around with a positive side and negative side to the molecule. Something has to happen for it to get that positive side and negative side. And that's why it's essentially a temporary sort of situation that occurs and a weaker sort of attraction. When we talk about, like we did earlier with dipole-dipole and polar molecules and hydrogen bonding, no matter what the situation, if you have something like water, because it's a polar molecule, the oxygen side of it and the hydrogen side can be negative and positive respectively, no matter what the situation. It doesn't need anything to occur for it to become positive, negative, or have a positive or negative side. For our non-polar guys that use these dispersion forces, they need something to sort of happen, either the shifting of their electrons to allow them to interact. They need somebody to kind of come up on them to cause their electrons to interact. And it's temporary, that eventually it will kind of go back to the way it wants to be, which is a non-polar situation where we have equal sharing of electrons. So that's really why this type of interaction, even though it technically is kind of the same thing, positive, negative come together, is a relatively weak intermolecular force because it's temporary. It needs something to happen. Anything that's polar, because it has a dipole moment, out of the box, it's good to go. It's got a positive side and negative side, no matter what situation, it's ready to go. It's ready to interact. These guys need something to happen to allow it to interact. Other questions? So our water, like I said, it's good to go, which is why it's polar. Something like CH4 would need something like this to occur and to allow it to interact. And again, that's why these are the weakest of all of them, these type of forces. So dispersion forces are typically how non-polar molecules interact with each other. And it is the weakest of all three of those forces. Any questions on that? Yeah. Pretty much anything that's non-polar, that's what's happening. That's how they sort of stay together. So for example, CH4, right, which is non-polar molecule, it would use dispersion forces. And that's basically what's happened when a bunch of CH4 molecules are together, basically. That is how they basically interact with each other. They're using those sort of temporary sort of forces to interact. Yeah. So in terms of solubility, the idea of sort of like dissolves like, which is the idea that things that are non-polar and non-polar, that's basically they can interact well with each other because that's how they interact with themselves. So they're able to interact with others. So as long as you have that sort of connection between, say, a non-polar and non-polar guy, they will interact using these forces. And same thing with the polar guys. As long as you have the polar and polar guys together, they're going to use either dipole-dipole or hydrogen bonding. But if you try to mix a polar and a non-polar, what's going to happen is they really won't mix. And for the short period of time, as we talked about, they maybe will mix just a little bit. And that's because everybody could use dispersion forces. So even polar molecules basically could use dispersion forces, doing that induced dipole type of situation. But over the long period of time, there's no way for that polar molecule to maintain that pretty good interaction with the non-polar molecule without the non-polar molecule kind of breaking apart and coming back together, which is why ultimately they really don't mix really well. Other questions? Now, speaking of dispersion forces, it does increase, the strength increases with molar mass. So the strength of a dispersion force increases with molar mass. So although dispersion forces are the weakest, if you're comparing two, say, non-polar molecules that basically both use dispersion forces, and you want to know which one would have, say, the larger boiling point or melting point, The one that has the higher molar mass would be the one that would be the strongest of the weakest. And the reason for that is if I have a high molar mass, that means I have more elements, more atoms. More atoms means I have more electrons. More electrons means there is a greater chance of polarizability sort of happening, the electrons being shifted, and also gives it a lot more places for them to interact with one another. So in terms of dispersion forces, you could rate the strength of the weakest dispersion force or intermolecular force by higher molar mass, stronger dispersion force, lower molar mass, weaker dispersion force. That's why, for example, something like methane is a small molecule, uses dispersion forces. And where do we find methane most of the time? Coming out of our thing when we light our Bunsen burner, right? When we do have gas in this building. So when we turn on the thing and we do have gas, methane is a gas, right? And a lot of organic molecules, which are non-polar, especially the first few, are also found as gases, things like methane, propane, butane, right? Those are all gases. And that's because they're basically small, they're organic, they're non-polar, and they're using these really weak dispersion force, which means it doesn't take a lot of convincing for those guys to go into the gas phase. So they're able to go into gas phase really well. And if you take organic eventually, that's also why they stick you in a fume hood when you use a lot of organic molecules, because they all, most of them, or a lot of them use dispersion forces, which means they could jump into the gas phase really, really quickly. So you don't smell it. They put you in a fume hood. They're sometimes referred to as being volatile. They're able to jump into the gas phase really, really easy because of that. Any questions on that? All right, so here's sort of a summary of what we just talked about. Just dipole-dipole interaction, again, is basically the major intermolecular force that polar molecules uses with other polar molecules and themselves. So this interaction can be with a polar molecule in itself or another polar molecule. Again, those are the ones that do not have the ability to hydrogen bond is going to probably use dipole-dipole interaction. Those that have the ability to hydrogen bond, which means you have a hydrogen that's attached to nitrogen, oxygen, or fluorine, will do hydrogen bonding. And dispersion forces are the weakest of all of them. That is really our non-polar interaction. And that is going to be temporary sort of forces. So the strongest in terms of intermolecular forces is going to be hydrogen bonding, followed by dipole-dipole. And again, our dispersion would be our weakest. So things that have hydrogen bonding or the ability to hydrogen bond typically will have higher boiling points and melting points because that's a really strong force that holds one molecule together with another. Those that have dispersion forces will typically have really low boiling points and melting points and are typically in the gas phase. Any questions on any of those things? And here's some pictures of those interactions. Again, our polar molecules, positive side of one, negative side of another. By the way, when a bunch of polar molecules sort of get together, they do try to maximize the attractive forces between a polar molecule and another one and minimize the repulsion forces. No matter what happens, especially as you get them into sort of the solid phase, there is going to always be sort of a positive side of one next to a positive side and a negative side next to a negative side. But what they will do is sort of vibrate around and move around to really sort of maximize more of the attractive forces and sort of minimize those kind of repulsion forces that occur between them. And this is, again, water molecule hydrogen bonding, as we talked about with ice earlier. Again, as this sort of hydrogen bond, especially in the solid phase, because of that strong sort of intermolecular force, it keeps those water molecules away from each other. And again, that's why we sort of see that lower density in ice versus liquid water. Here's our instantaneous dipole, which is just that temporary difference in how the electrons sort of move. So this guy's electrons decides to go this way, going to affect this non-polar molecule. Now they both have a positive side and a negative side, going to allow them to interact with one another. So let's talk a little bit about evaporation and condensation here. We talked about it earlier. Vaporization or evaporation, again, is the process where we go from liquid to gas. And that happens at the normal boiling point of a substance. And obviously, as we go the opposite way from gas back to liquid, that is condensation. The vapor pressure is the pressure of the gas above a liquid, because at the surface of a liquid, that's a very badly drawn surface of a liquid. I'll go that. There is a constant sort of exchange of molecules jumping out of the liquid into the gas phase and dropping back into the liquid as they sort of slow down. And the vapor pressure is basically above that liquid. How many gas molecules you have, right? Gas causes pressure. So the more gas molecules above the liquid, surface of the liquid, the higher the vapor pressure is. The lower the gas molecules, the lower the vapor pressure would be. Something that has a weak intermolecular force is going to allow those guys to escape the liquid phase and go into the gas phase easier, which means there would be greater number of gas molecules above the liquid and would have a higher vapor pressure. And again, as I mentioned, that sometimes what is referred to as being volatile. Those with a much stronger intermolecular force is going to be harder for those liquid molecules to escape to the surface, which means there's going to be less gas molecules above the liquid and would have a lower vapor pressure because of that. As we'll talk about maybe in a later chapter, this is also why we have just a little spill of liquid on the counter. We have that evaporation and vaporization occurring, or condensation occurring. But what also happens, right, if it's open, is there's air, and the air blows away the guys that are evaporating, so they can't come back to the liquid part. And eventually, right, your little drop, right, evaporates over time. Doesn't happen when you put it into a container, right? Much longer for liquid in a container to evaporate, but it will, because a lot less of it can get out and blown away. Even less when you put a lid on it, right? Less of it can escape, so it stops the evaporation process. So another sort of example that happens when you do put a liquid in a container and you do put a lid on it, for example, when you first kind of put it in there, what's going to happen is you're going to have an incredible amount or a higher rate of evaporation occurring. So eventually these guys are going to evaporate. But again, with the lid there, they pretty much have nowhere to go, which means they're going to drop back into the solution. And eventually what will happen is the rate of evaporation will equal the rate of condensation in this sort of situation. And what you typically will notice, as you can see in the picture, is you'll probably see when it comes to equilibrium that the liquid level has come down a little bit. And that's because initially when you put it in there, a greater amount of evaporation occurs, but then condensation comes back. Eventually the rate of both of those will equal each other. And that usually results in sort of a little bit lowering of the liquid in there, because now we have a lot more gas molecules above the liquid than we started with, in vapor pressure as well. So all these gas molecules above the liquid here would be causing the vapor pressure in this situation. All right. Just finish up with a little bit about types of solids. Good talk. So there are many different types of solids. Solids are typically either a crystal type solid, where we have really organized, regular arrangements of how they're put together. Ionic solids, for example, are very, very organized. There's long range order. As you'll learn in 1A, there's such long range order. You could rebuild the solid by just simply taking a little portion of it, and it repeats so often that you can build it back up together. What I mean by that is, and you'll learn in 1A, is you could take like a sampling of a solid, like a unit, it's sometimes referred to as a unit cell. And basically by just restacking this unit cell side by side and back to back, you'll be able to recreate the solid that was there. For example, take a unit cell that looks something like this, and you basically stack one up on top. Stack one over here. And now I've just rebuilt my sort of solid there by just taking that little piece. So they're very repeatable. They have long range orders, sometimes referred to as well. molecular solids like sucrose as well. A third type of crystalline solid is an atomic solid, and it contains only an atom of one element, like graphite, carbon, boron, silicon, and all the metals kind of come together in an atomic solid. And here is a ionic solid, and again, you can see these represent the ions. The bigger circles represent the negative ion, right? Because they gained electrons. Smaller guy is the positive guy, right? Because they lost electrons. And again, they rearrange themselves in a way that maximizes that attractive forces between each other and sort of minimizes those repulsion forces together. So here's our different ones. Components are ions in ionic solid. Molecular solid or molecules, and atomic solid are atoms of those guys. This is some arrangement here of some different molecules. We have our diamond, by the way, an allotrope, which I think we might have talked about before, which is basically the same molecule, same element, but different sort of arrangement. So like carbon, for example, that is can be a diamond like we see here. It can be graphite where the carbon's layered out. So different sort of arrangement of the same elements give you allotropes. Here's our water molecules, right, which are molecular solids that come together, and that's definitely an ice. And again, you can much see those big open spots there. So bonding in solids, ionic solids are held together by strong electrostatic attractions. They have high melting points, and that is typically what happens with an ionic solid. You could heat the heck out of it. It will not jump into the gas phase because it's held together by that intramolecular force, those electrostatic attractions, or they'll just start to melt. Molecular solids are held together by dipole-dipole forces or dispersion forces. They do melt at lower temperatures. So for example, water, right? We know we just got to heat it up to 100 degrees and it's going to start to evaporate as well and go off into sort of the gas phase. Now, an alloy is a substance that contains basically a mixture of elements. And has metallic properties. There's basically a substitutional sort of alloy, and that basically is what it sounds like. Basically, is the host metal is replaced by similar metal sort of in its place. Like sterling silver is 93% silver, 7% copper. So you got some copper guys in the place of all the silver. An interstitial alloy is formed by holes that are packed tightly with atoms like steel. Carbon atoms in the holes of the iron are put in there to sort of reinforce it. And you kind of substitute some in between different elements or atoms. And here's an example of that. Here's brass, where we got some zinc in with all of our copper. And here's steel, where we put sort of carbon in between each of those sort of iron sort of molecules or atoms. And that is that chapter.